All right, guys, it's time for some fun with math. And so today we are going to talk about something called absolute convergence. And then we're going to learn a new test, the ratio test, and we'll save this root test until next time. So we got two things I want to do today. All right, so let's talk about this absolute convergence first and what the heck it is and why it's important. So what is absolute convergence? So a series, so here's our series, sum equals 1 to infinity, the a sub n's. This thing is said to converge absolutely if the sum of the absolute values converges. So the idea now is basically we've been working with series that always have positive terms. And so if you take a look back at that integral test, and then those comparison tests, right? So there are two comparison tests, the comparison test and then the limit comparison test. If you look at both of these, they both have one restriction. The series has to be positive. So we're looking only at positive series. Now, a lot of series are not positive. Some go positive and negative in the sense that the terms could be negative. So the question becomes like, what do we do if we have something like, I don't know, 1 minus a half, plus a third, minus a fourth, plus a fifth. So not all the terms, minus dot, 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 not all the terms are positive. Some might be negative. The problem is we can't use the tests that we've learned, at least the integral test and the comparison test. You could use a divergence test on a series that's not positive. But of course, this series here, notice the terms are going to 0. So the divergence test won't apply. So is there some way that we can figure out if this series converges or diverges? And so it turns out that this idea of what's called absolute convergence can be used. And so the reason why it's important is because there's this little theorem here, and it says what? It says if the sum of the absolute values of the a sub n converges, so that means they converge, that series converges absolutely. So if that series basically converges absolutely, what is that going to imply? That implies normal convergence. It implies that the series without the absolute value on it, on the terms, will converge. And so absolute convergence basically implies regular convergence, right? So if it converges absolutely, it's going to imply this thing is going to converge, right? So absolute convergence implies regular convergence. Now, why does that work? So this is actually kind of cool. And again, it's a very simple argument. So check it out. So here's my n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. That's my n. And we're going to focus on this series here, the sum of the a sub n's. And so a sub 1 is just, let's say it's this height here, and let's say it's positive. Let's say a sub 2 here, and let's go back and make these. I'm going to color this. So I'm going to make the positive stuff green. So let's say a sub 1 is positive, so there's height a sub 1. And of course, a sub 1 is the same as that area. Let's say a sub 2 winds up being negative. So here's a sub 2 right here. That's that height. And so it winds up being negative. And then let's make a sub 3. Let's also make it negative, just for fun. So, and then we'll kind of make a sub 4 positive. Why not? So I'll make that one positive, a sub 4, that height there. And then let's make a sub 5 negative again. So here's a sub height, a sub 5. So it gets that area there. And then plus dot, dot, dot. So what you can do is you can take this series, the sum of these a sub n's, n equals 1 to infinity. And if you want, you can kind of split it up into two pieces. You can split it up into its positive piece and into its negative piece. So you can kind of look at this as a sum when the a sub n's are bigger than or equal to 0, let's say. So there's part of it. And then you can add, so then plus, and then you have the negative pieces, the sum, the a sub n's when they're less than 0. So you kind of, if you want to think about it, you can just split the sum up like that. Now I claim that if this sum here, if we assume this thing converges absolutely, so if this converges absolutely, I claim it should clearly imply that this sum here is also going to converge. So it's kind of like absolute convergence is a stronger convergence than regular convergence. Now, why is that? So let's suppose that the sum of the absolute value of the a sub n's n equals 0, n equals 1, I'm sorry, to infinity. Let's suppose it converges, right? So it converges absolutely. So that thing actually goes to some sort of number. So what does that thing look like? Well, you can just kind of trace it out here. Here's a sub 1. So absolute value of a sub 1 and a sub 1 are the same because they're both positive in our picture. Absolute value of a sub 2, it just flips over here. So that's absolute value of a sub 2. But it's the same rectangle. And a sub 3 is right here. And again, that's absolute value of a sub 3. And it flips over. And then a sub 4, it's exactly the same because it's already positive. And that's equal to absolute value of a sub 4. And then you can see here also, 4 is on here, always get messed up. And then I also see that a sub 5, or absolute value of a sub 5, looks like that. And so the claim is that the blue areas, when you add them all up, right? So all these blue areas here, if you add them all up, it's going to be finite, right? That's what it means to converge absolutely. You take the sum of the absolute value of the terms. Well, check it out. Doesn't that mean that the green areas have to be finite too because they lie underneath the blue areas? So that means this is finite. Well, let's just say finite. I say finite meaning converges. That means that converges. And then the red areas, now they don't lie underneath the blue areas, but they're the same value, but they're just the negative. So these two areas are basically exactly the same. One is just a negative of the other. And so again, they kind of like fall below in some sense, the blue areas. So they also converge. So these converge too. And again, it's really the same sort of argument. It's just the red quote areas are negative, whereas the blue areas above them are positive. But you add the positive, they're all positive. One's above them, you add them together. It has to converge because the whole blue areas converge. And then so the red areas then, even though they're negative, it's just adding a bunch of negative numbers and they're going to converge the same number as the blue areas above it, just going to be a negative number. So they're also going to converge. And so now what happens here? If you add something that converges plus something that converges, then this has to converge. So absolute value, so that has to also converge. So absolute value, or some of the absolute values of the a sub n's, if they converge, that implies the sum n equals 1 to infinity of a sub n converges. All right, so if these converge, so these sums converge, that sum converges, that implies that the regular sum without the absolute values on it is going to converge. So it's kind of a nice little argument. And again, it's all kind of like a line above, line below argument. It's the same thing almost every single time. Let's take a look at some examples of how we can use absolute convergence to show if a series converges or diverges. So on this one here, let's look at part A. Notice we have this series, and notice how the negatives work. It goes negative, negative, positive, positive, and then negative, negative, and it's go positive, positive. And so this is our series S. So let's call it S. S equals this. And then to see that this series actually converges, what we're going to do is we're going to look at the sum of the absolute values. And so I use this little notation here. Sort of like the absolute value of S, but it's not really the absolute value. It's a sum of the absolute values. And so what does this look like? Well, if that's negative, that's positive 1. And then that's negative 1/3, so it's positive 1/3, then positive 1/9, and then positive 1 over 27, and then positive 1 over 81. So we're adding up all these plus positive 243. And that's equal to then the sum. And so then notice each of these terms here, let me change colors. Each of these terms here, that's going to be basically 1/3 to the 0. And that's going to be plus then 1/3 to the 1. And then plus 1/3 to the 2. And then plus so on and so forth. And so this is just a geometric series. N is equal to 1 to infinity. Oh, sorry, 0 to infinity. And then that's 1/3 to the n. And we know that this converges. So it converges because it's a geometric series. And it's a geometric series with what? With r equal to, or the absolute value of r, I guess, equal to 1/3, which is less than 1. And so what can we conclude now? So by that absolute convergence theorem, basically, that little picture we drew, we can say, therefore, S converges absolutely. which implies S converges. All right, so if S converges absolutely, it automatically converges because absolute convergence is absolute, right? It's like a super strong convergence that implies regular convergence. All right, so before you think too much, let's do it again. So check this out. Again, it's super easy to apply, really. So S is equal to, and so we have the sum n equals 1 to infinity of -1 to the n divided by n squared. So we're going to look at sort of like this quote, quote, absolute value of the sum, although I'm just doing the absolute value of the terms. So what does it look like? The sum n equals 1 to infinity, and we just slap an absolute value on the term. So -1 to the n over n squared, and take the absolute value of it. And then what happens when you take the absolute value of this? It just makes it positive. So the -1 just goes away. So that's just equal to the sum n equals 1 to infinity of 1 over n squared, which we know that converges. Why? Because it's a p series with what? With p equal to 2, which is bigger than 1. Therefore, our series S converges absolutely. And we know absolute converges, remember, it's absolute, right? So it implies S just converges. In fact, that absolute convergence theorem, if you wanted to, you could actually call this, you could cross off that theorem if you wanted it. We actually call it another test if you really wanted to. Right? So you could say it converges by the absolute convergence test, although we usually don't do that. I think we have enough tests basically, and it's not hard to remember that absolute convergence implies our regular type of convergence. All right, so those are the kind of problems we'll be doing. So whenever you see something that has maybe some negatives on the terms, just remember you might have to test it for absolute convergence, and then you can conclude if it does converge absolutely, that it converges. Now, if it doesn't converge absolutely, it doesn't mean that S diverges. So that's very important. So there are series that are not absolutely convergent that do converge. We're going to learn about those next week, basically, and that's called conditional convergence because it depends upon the condition of the pluses and the minuses, like where they're actually placed. All right, before we get too deep in that, let's switch gears just a little bit and let's talk about one of these tests. So we're going to talk about what's called the ratio test. Where there's a ratio test and the retest, and they kind of go together, as you can see here. There's a little curly bracket. And these tests, what they actually test for is if a series behaves like a geometric series. So this is a test to see if a series behaves, in some sense, geometrically. So we know what a geometric series is, but what is it in essence? So in essence, if you look at a geometric series, here's what it looks like. Sum n equals 1 to infinity of a times r to the n. And let's just write that out. So that's a plus ar plus ar squared plus ar cubed plus dot, dot, dot. And so what a geometric series really is, its essence basically, is if you take the next term and divide it by the term before that, notice what always happens, so like ar cubed divided by ar squared. So what happens is you always get back a constant. And so what a geometric series in essence really is if you take the ratio of the terms and you get back a constant, then it has, in some sense, the essence of a geometric series. And so this is first captured in the ratio test here. And so what does the ratio test say? I think I'm going to go to another slide here, guys. I guess not. I guess it's over here. So I'm missing a slide, but that's okay. So the ratio test says what? Just consider the series, the sum of these a sub n's, and if you take the nth plus 1 term and divide by the nth term, and you would use the absolute value because this is actually a test for absolute convergence. So you take that limit as n goes to infinity. What happens to that ratio? If you wind up getting out a number here, and that number is less than 1, then your series will converge absolutely, which of course implies it just converges too, by what we just did before. If that r is bigger than 1, it turns out it diverges, just like a geometric series. So remember, geometric series here, this thing is going to converge to a divided by 1 minus r as long as your absolute value of r is less than 1. And so that's what you're basically saying here, because you already took the absolute value of this thing, so you know it's going to be positive. So if r is less than 1, it's going to converge absolutely. If r is bigger than 1, it's going to diverge. So that series is going to diverge. And if r equals 1, then we have to say the test is inconclusive. We're not quite sure what's going to happen. And then it has a kind of a partner over here, the root test, which we're not going to talk about today. We're going to save to next time. So let's take a look at the problems we're going to do. So how does the ratio test work? We're not going to talk about why it works today. Today, we're going to talk about how it works. So here are the series that we're going to use the ratio test on. So we have A, B, and C. And what you want to notice is we have a factorial. We have sort of a geometric thing, 3 to the n, and then we have just kind of like a p-series stuff, right? So no geometric thing, no factorial thing. And in each of these cases, you're going to see that this one actually will converge. This one actually will diverge. And I actually know that because the geometric series is an exponential term is much stronger than a square term. So this thing is actually going to go off to infinity. But that's how I see that it diverges, right? So that's actually going to diverge. And this one is actually going to be inconclusive, I think. I don't think we're going to be able to tell what happens on that one, but we'll see, because we're going to run the test here on each of these. So let's come over here, and we're going to use a ratio test to see if this thing, the series converge or diverge, or we should also write, or I guess it could be inconclusive. There's actually 3 cases that could come up. And so how do you do this? Again, this is super easy to do in the end, and the ratio test is like your best friend. It's a really important test. It can work on any series. It could be positive, it could be negative series, doesn't matter, any series. And so here we'll let a sub n be equal to, and so it's just our terms, so 1 over n factorial. And so they're going to take the limit as n goes to infinity. And here, I often write this out. So absolute value of a sub n plus 1, that n plus 1's in the subscript, and then divided by a sub n. So you're just looking at the ratio of 2 terms, the next term to the previous term. And so what does that equal to? So we just write down the limit as n goes to infinity, absolute value of 1 over, and then this one, the nth plus 1 term, is just wherever you see an n, you're going to put an n plus 1. So it's n plus 1, and then factorial. And I'll write the 1 in green too. And then we're going to divide that by the nth term, and so that's just 1 over n factorial. Make that absolute value a little bit longer, put it on the other side. And so what does that equal to? So it's equal to the limit as n goes to infinity. And then when you divide by a fraction, we just multiply by the reciprocal. So we have here 1 over n plus 1 factorial, and then times an n factorial over 1. And so that's equal to the limit as n goes to infinity. And I'll kind of clean this up. N factorial over n plus 1 factorial. And now here's where it gets kind of cute, basically. What happens next? Well, you can actually rewrite n plus 1 factorial and n factorial out and see how they can't. So, and there are a couple ways to do this. I'm going to do it the long way here right now, and we can do it the shorter way later in class. So here, this is like n times n minus 1 times n minus 2 dot, 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 and it goes down to 3 times 2 times 1. So that's a definition of n factorial. And then n plus 1 factorial looks like this, n plus 1, and then times basically n factorial. So n times n minus 1 times n minus 2 times dot, 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 and then 3 times 2 times 1. And so you see basically almost everything is going to cancel, right? So the n's cancel, the n minus 1, n minus 2, the 3's cancel, the 2's cancel, the 1 cancels. And so that's equal to then the limit as n goes to infinity of 1 over and then you have n plus 1 here. And now we're going to let n go to infinity. And so what do we get? 1 over infinity plus 1, which equals 0. And that's less than 1. So remember, 1 is like the cutoff point. And so if it's less than 1, what do we say? Therefore, our series, let's give it a name, S. So therefore, S converges by the ratio test. There it is. All right, and so that's how you run a ratio test. You just look at the limit as n goes to infinity of the consecutive terms, right? So a plus 1 divided by a sub n. Make sure you do absolute value. Although this one, we could drop off the absolute value because everything's positive. And then see what that limit is. If it's equal to a number less than 1, you see that it converges. Actually converges absolutely, right? But of course, absolute convergence implies regular convergence. So here I usually just write S converges. You can write S converges absolutely by the ratio test if you want to. Okay, let's go to the next one, B. And so in part B, we have this series. So we'll call this S. And what we'll do is we'll look at these terms here. So let's just identify the terms. So a sub n is equal to 3 to the n over n squared. Hold on one sec. Sorry, guys, my dog was getting into some paper there. All right, so identify your term. And then what do we do next? We're going to run this limit. So you take the limit as n goes to infinity, and I want to look at the nth plus 1 term divided by the nth term and take the absolute value of that. And again, if you want to understand what's happening, you're basically testing to see if it's kind of behaves geometrically in the end. So if you get out a constant, what that's telling us is that this behaves like a geometric series, not in the beginning, but in the very, very end. So what is this equal to? So limit as n goes to infinity, we have the absolute value of what? So we're going to find a sub n plus 1. So wherever you see an n, you're just going to plug in an n plus 1 now. And so you have 3 to the n plus 1 divided by n plus 1 quantity squared. And then that's all divided by, and now you do the nth term here. And so you just copy this down. So 3 to the n divided by n squared. Let's close off that absolute value. This will be equal to the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 quantity squared. And now, since you're divided by a fraction, we just multiply by this reciprocal. So that's n squared over 3 to the n. And so that's going to be equal to the limit as n goes to infinity of what? So now 3 to the n plus 1 is really a 3 to the n times 3. So I'm going to write that out. So it's 3 to the n times 3, and then times another n squared. And then on bottom, I'll rewrite that 3 to the n over here on the right, I'll write on the left, so it's closer to that 3 to the n on top, and then n plus 1 quantity squared. And so I did that because it's very clear now the 3 to the n's are going to cancel because you have one on top and one on bottom. And so this is the limit as n goes to infinity of 3n squared divided by, and if you want, you could multiply that out, but if you know that's just n squared, it's fine. I think maybe we'll multiply it out. So that's n squared plus 2n plus 1. And so now I see what's going to happen. Because I'm going to infinity, I can cross off the 2n and the 1. And so it'll be equal to the limit as n goes to infinity of just 3n squared, so 3 times n squared, divided by n squared. And very clearly, the n squareds then cancel. And then remember, what's the limit of a constant? It's just the constant 3. And that's fine. You can just write equals to 3 there. Now, this one, though, is not less than 1. It's greater than 1. So what do we conclude now? So therefore, we know our series does what? It diverges. So therefore, S diverges by the ratio test. And basically what this is saying is that this geometric series, not in the beginning, but in the very end, behaves like the sum of 3 to the n and equals 0 to infinity. That's what that one behaves like. Whereas before we got 0 out, so it's kind of like it's like a geometric series, like with almost like a 0 to the end. Of course, it's not quite 0 because it's a limit, but it's saying it's highly geometric in the end. Okay, what's next? We have one more left to do, I think. Let's look at this one. All right, so here's our series S. And of course, we know this diverges. We know it diverges because it's really a p-series with p equal to 1, but we want to use a ratio test on it. I want to use a ratio test on this because I want you guys to see, basically with p-series type series, like series where you have like a polynomial on top or a polynomial bottom, the ratio test is no good. It's really good for factorial stuff. So when you have n factorial stuff, or when you have geometric stuff like 3 to the n, or a 4 to the n or something, or 1/3 to the n. So when you have geometric stuff and factorial stuff, the ratio test is pretty simple to apply and usually works. But if you just have polynomial stuff on top and bottom, it doesn't usually work out. You're usually going to get, you're always going to get out 1 if that's the case. So let's just check it out. So what's a sub n? Which means it's going to be inconclusive. So a sub n is equal to 2 over n. Let's run our limit on it. So it's the limit as n goes to infinity. You take the nth plus 1 term and divide by the nth term. And so this is equal to the limit as n goes to infinity. And so remember, all we're going to do is find the nth plus 1 term. So wherever you see an n, you just plug in n plus 1. And so it's 2 divided by n plus 1. And then divide that all by your a sub n here, which is just 1 over n. Oh, and I guess we should put the absolute value on there. All these absolute values can be dropped off because everything's positive. You will see later on the absolute value turns out to be very important, not in this section, but in the next section when we talk about those power series. All right, so this is the limit as n goes to infinity of 2 over n plus 1 times, and we multiply by the reciprocal, so n over 1, which is equal to, ooh, I messed up something, guys. I know it's going to diverge, right? So that's a 2 right there. So that's an n over 2. And I can drop off the absolute value because everything's positive. And so what's this going to be equal to? This is going to be equal to the limit as n goes to infinity. I have a 2n on top, and then I'll multiply through by the bottom by 2. So I have a 2n plus 2. Because I'm going to infinity here, I can cross off the 2 because that doesn't really matter on the bottom. I just keep the leading terms of my polynomials. So 2n's leading term on top, 2n's leading term on the bottom. Very clearly, the 2n's are going to cancel and leave me with 1. So it's a limit as n goes to infinity of 1, which of course is equal to 1, which is equal to 1. And so therefore, my S, oh, we don't know what is it. Therefore, we can write the ratio test is inconclusive. So inconclusive, which means we don't know with that test. Now, we do know it's a p-series with the p equal to 1, so it's going to diverge. But that ratio test doesn't give us any information whatsoever. And that's it. All right. And so hopefully you kind of see, like, I set the problem up the same way every single time. And the ratio test we'll be doing for really the remainder of the semester. All right. That's it, guys.